Okay, great. Welcome, everybody, to our first session on quantum cryptography. Our first talk is on tracing quantum state distinguishers via backtracking by Mark Chandry, and Mark will give the talk. Take it away, Mark.
Thank you. So let's start with a bit of background. So let's see what trader tracing is. So in classical trader tracing, we imagine a content distributor is sending encrypted broadcasts to a number of users. And what we're worried about is that some of these users may be malicious, and they may pool their secret keys together and create a pirate decoder that can decrypt ciphertext, and then they post it on the internet or something like that. There's nothing we can do to really stop this, but we can hope that we have a tracing algorithm that takes such a pirate decoder and is able to accuse at least one of the malicious users while making sure never to accuse an honest user. So how does classical trader tracing work? So here's an abstraction that we can think about. So we imagine that there's a family of ciphertext distributions indexed by the number 0 to n, where n is the number of users. So the distribution d sub n is going to be the distribution of honestly generated ciphertext. All the other distributions will be, malicious or sampled in some other way. And then for any potential decoder, we have the quantity p sub q, where q is the index of the distribution. P sub q is going to be the success probability of the decoder on that distribution. The guarantees we have, well, by the assumption that the decoder works, we know on honestly generated ciphertext, the success probability must be high. So if Pn is much greater than 0. And then we have some cryptographically enforced properties, namely that P sub 0 is always close to 0. And also P sub q and P sub r, the success probabilities on two different distributions, must be close if there is no user index between the subscripts on those P's. Okay. There's also more general tracing structures used, such as with fingerprinting code-based trader tracing. But for the purposes of this talk, we'll focus on the structure described in this slide. So what you end up getting is this kind of graph of P sub q relative to q. And the honest users, where you have an honest user, the graph must stay relatively constant. And the only place where it's allowed to deviate is just to the left of any of the malicious users. And that's who we're trying to find. So the way classical trader tracing typically works is it's looking for these gaps in the success probability. So the tracing algorithm will query on ciphertext distributions, will query the decoder, see its success probability, and look for these gaps. In the case where n is polynomial, you can just do a linear scan, and it's really easy to find where the gaps are. Now, you could imagine n being super polynomial. So you still have a polynomial number of users, but their identities belong to a super polynomial space. And here again, in the classical setting, you can solve this with a variant of binary search. So why are we interested in super polynomial? Well, one is we showed that if you have super polynomial identity spaces, you can embed arbitrary info into the key. It also relates to this problem in the obfuscation setting of proving the equivalence of something called indistinguishability obfuscation and differing inputs obfuscation. There's a very similar algorithm that was actually the inspiration for the tracing algorithm that shows that two of these notions are the same. But again, it works in the super polynomial domain setting. And for other trader tracing structures like fingerprinting codes, it's sort of inherent that you are looking at a super polynomial domain. Okay, so now let's enter the quantum setting. And the problem we're going to be concerned about today is when the pirate decoder produced by the malicious users, it actually contains a quantum state. And we still want to be able to trace such quantum state decoders. The problem is that in quantum mechanics, when you observe a quantum state, you potentially disturb it. And maybe you change it to a different state. In our case, as the tracer is trying to learn these P sub q values, it's actually affecting the quantum state and potentially changing it. Maybe it's actually destroying it. And after some number of queries, maybe the quantum state decoder actually explodes and stops working. And so what we need to do is we need to be able to somehow make queries to the decoder even when the state is changing over time as we're querying it. And we still want to be able to extract information that allows us to accuse malicious users. So in some prior work, we solved this for the specific setting of a polynomial domain size. So we have the same setup where you have this family of distributions. But now, as we said, the probabilities of success of the decoder are changing over time. So we're actually going to note that there's a specific query sequence, and that the probability of decoding actually will depend on where the query is in the query sequence. And now in the prior work, we showed that there are still some guarantees that you can get. They look somewhat similar to the guarantees in the classical setting, but they're a little weaker. So the one guarantee is that if the first query is on n, the honest ciphertext distribution, that the observed success probability still must be high. So this is kind of the same as the classical setting, except this guarantee only applies to the very first query. Subsequent queries, there's no guarantees. For the cryptographically enforced properties, we still have that P0 is 0 always. This one's the same as classical. And then the last one's the most interesting one. I call this local consistency. And it says that the two probabilities are close if there's no malicious user between them, but only if we're considering adjacent queries in the query sequence. If you're trying to look at queries that are 2 apart or 3 apart in the query sequence, it doesn't matter if there's an honest user or not between them, there's no guarantees. So it's only for adjacent or subsequent queries in the query sequence that we have this consistency guarantee. So in this work, we showed that this is enough to do the linear scan. Turns out you can just take the classical tracing algorithm and it just works. But it fails for binary search. And actually, there's a really simple proof that with these guarantees, you can only ever extract a log amount of information. And basically, the reason is that you can always have 1, 1, 1, some number of ones followed by some number of zeros be consistent with the rules of the tracing game that I described on the previous slide. And if you only have a polynomial length query sequence, that's just a bunch of ones followed by a bunch of zeros, there's only a log amount of information, namely the position of the switch from ones to zeros. A more recent work by Kitagawa and Nishimaki, they're working not in trader tracing, but on watermarking, which is very similar. And in their setting, they were actually able to guarantee global consistency, but they weren't able to handle collusions, or they didn't try. But it seems like their techniques are really limited to the case where there's no collusion. So this is basically where things stood. We had in the trader tracing setting where we have collusions that you could only do this linear scan. And then in another setting where there are no collusions, you can do better. So in this work, we make some progress on this. And basically what we show is something I call single-step rewinding, which is, so we have the same 3 rules we had in the quantum setting before, except they add one more rule that applies now for queries that are 2 apart in the query sequence. So there's one query in between them, the queries are 2 apart. Before, there was no guarantees at all if the queries were 2 apart. And here, what is the guarantee? It says that if I have the same query twice, separated by only at most one query in between, but it's literally the same query, that the success probabilities have to be close. Right? So that's the new guarantee that we give. It's a very mild guarantee, but it's something that was not handled by the prior work. And note, if you're looking at queries that are more than 2 apart, then there's still no guarantees. I won't really go into the proof. The proof uses these techniques called quantum state repair that we developed in a completely different context of rewinding for argument systems. But we were able to adapt those techniques to the setting of trader tracing to guarantee the single-step rewinding promise. Okay, so now the question is, how do we actually take advantage of this one extra property that we have? We know without the property, we're only able to extract log bits of information. So how do we use this extra property to extract more? And what we do is we develop some algorithms that you might call hesitant algorithms. And basically what they're doing is, so they start with this high success probability on a ciphertext distribution. And as they're going, they're always going to maintain that they're sort of querying on things with high success probability. Now, maybe they query on something and they get a low success probability. At that point, they back off and say, okay, I'm just going to go back to the previous query where I knew I had a high success probability before. And because there was only one query between the previous query and now, and it's on literally the same exact query, we know that the success probabilities are the same. So we're able to always guarantee that at least one of the last two queries had a high success probability. Okay, and this is going to be the general idea. So let's see how this works for binary search. So binary search is going to start off just like you would expect. So we first query on n. We see that we get something high. This is, again, by the assumption that the decoder works. Now we choose our pivot to be at n/2, and we query on n/2. Now, there are two cases. So in the first case, we see something large. We query on n/2, and we see a high success probability. In that case, actually, we do what you do in classical binary search. You recurse left on the interval 0 to n/2. Okay, not so interesting. The more interesting case is when you actually see that the query value on n/2 is low. If the success probability is low, the problem is if we were to continue and trying to recurse at 3n/4, because of the guarantees we have, it's actually possible if 3n/4 was low. Might be that all future queries that we send to the decoder result in a low success probability. So what we do is we backtrack. We go back to querying on n. So we set the third query to be the same as the first query. And by our single-step rewinding guarantee, we know that we must get a large success probability because these were only 2 apart. So now we query on n. We get a high success probability. And now we recurse right by querying on 3n/4. But that's not all. We're not done. And the thing is that as we queried on n a second time and then queried on 3n/4, now it could be that the success probability on n/2 changed. Right? The last time we queried on n/2 was now 3 queries ago. And so the success probability on n/2 maybe it became high. If it became high, that's a problem for proceeding with the standard binary search, because a standard binary search would try to recurse on n/2 on the interval n/2 to 3n/4. We know that there's a user in there that we want to accuse. But if the success probability on n/2 were high, we might not ever find any jumps in this interval anymore. We would have found a jump initially, but because we kind of did this backtracking thing, now there's potentially no more jumps in the interval n/2 to 3n/4. And so we can't actually recurse on this interval and be guaranteed anything comes of it. So our solution is, instead of querying on n/2, 3n/4, we just query on the entire interval to the left of 3n/4. So we just recurse on this interval. We haven't divided things into quite as small of intervals, but we've still made progress from the original interval 0 to n. We know that we can find a user in 0 to 3n/4. And we show that you can actually recurse, and the simple rules that we have for our tracing will enable you to actually find a user. So we show that an algorithm finds a malicious user in k log squared n steps, where k is an upper bound on the number of malicious users. So this is a bit worse than the classical binary search, where it was only linear in log n instead of quadratic. Okay, so for results, so we apply this to the tracing structure that I described, and we get collusion-resistant traitor tracing that allows you to embed arbitrary identities. Under various assumptions and depending on which assumption you're willing to make, you get different parameters. So under indistinguishability obfuscation, we're able to get all parameters optimal. Under the assumption of public key encryption, we're able to solve this, but the parameters grow with the number of users. We also solve the equivalence between IO and DIO with quantum auxiliary input, where the number of differing inputs is polynomial, providing a quantum version of the same classical result. And then we turn to combinatorial traitor tracing schemes, which are based on things called fingerprinting codes. And there we can show, under the assumption of public key encryption, we get collusion-resistant traitor tracing with constant size ciphertext, but the other parameters grow with the number of users. And we get the bounded collusion setting, we get traitor tracing also against quantum decoders, but now the parameters grow with the collusion bound, but independent of the total number of users. Okay, and for these last two, we actually needed to develop a new tracing algorithm for fingerprinting code-based traitor tracing that obeyed the rules that I described, but you know, it's not binary search based. We had to do a different kind of tracing algorithm. And then I just wanted to conclude by saying that there seems to be a barrier to generically lifting classical tracing algorithms to quantum results. So you might hope, like, we've now replicated many of the classical tracing results in the quantum setting. Maybe there's just a fully general theorem that says if you have any classical tracing algorithm that works against classical decoders, you can upgrade it to an algorithm against quantum decoders. And we show that this is likely not possible. We show that basically we don't give a traitor tracing scheme, but we show that there is some setting where if you follow the classical rules, there's a solution. But if you follow the quantum rules, as we gave in this paper, even with the single step rewinding, that you can't solve it. So probably this says that there's no generic result to lift classical tracing algorithms to the quantum setting. And that's it. Thank you.
We have some time for questions.
Thank you for the talk. Just to clarify this one-step rewinding. So you can make a subsequent query after you repair, and you can repair again. So you can make query, rewind, query, rewind.
Yes, yes. You can repair as many times as you want, but you're only allowed to repair one step backwards from where you are. So you're only allowed to repair you're allowed one query in between, and you can repair one step more. But you can do it as many times as you want. You can do it later. You can repair at different points, but you're just always repairing to one step behind. Yep.
Okay, if there are no other questions, let's thank our speaker again.
Okay.
Okay, great. Our next talk is Black Hole Radiation Decoding is Quantum Cryptography by Zvika Brakersky, and Zvika will give the talk.
Thanks.
Okay.
Hi, everyone. So this talk is about connection between quantum information aspects of high energy physics and cryptography. In particular, we're going to talk about radiation from black holes. So what's a black hole? So it's a region in space that has some interesting properties. In particular, if you create a black hole and you just leave it to be, it's going to start emitting radiation. It's going to emit radiation, and it's going to shrink in the process until in the end, it's going to evaporate completely. Now, if we just think about such a black hole in some point in its life, we can divide the universe into three parts. One, the radiation that's been emitted in the past from the black hole. We're going to call this R. The second part is the outgoing radiation in this moment in time, which we're going to denote by B. Now, we care about the information content in this radiation, so we're going to think about this radiation as being composed of qubits. In particular, we're thinking about it as being emitted one qubit at a time. So this subsystem B just contains one qubit. The third part of the universe is the inside of the black hole, and we denote this by H. Now, in total, H, B, and R constitute the entire universe, and this is just a pure quantum state. Now, another thing that, well, I want to say we, but physicists know, is that if you're emitting sort of radiation outside, for every qubit of radiation that you emit, there's going to be a maximally entangled qubit that's going to stay inside the black hole. It's going to fall into the black hole. So you can actually think about this radiation as sort of EPR pairs that are generated near the boundary of the black hole, and one of them goes out as radiation, and the other falls in. These are these entangled modes. So if you think about it, this actually creates a problem with time. So the one thing that we said was that if you look at this qubit B, then it's maximally entangled with the inside of the black hole, with H, because of this infalling entangled mode. On the other hand, I said that the black hole sort of emits radiation and it keeps shrinking. which means that in some point, the black hole is just not going to have enough entropy to be entangled with all of the radiation that it's already emitted, which means that at some point, the outgoing radiation B needs to be maximally entangled with the old radiation R, just from entropy considerations. And that's a conundrum, but physicists are pretty good with these things. And they were saying, well, look, if B is entangled both with R and with H, and R is outside the black hole and H is inside the black hole, that's kind of like, Clark Kent and Superman, right? They're never at the same place at the same time. So maybe they're the same system. And this satisfies them for some reason, until this firewall paradox was introduced. So Al-Mahiri, Merloff, Tulchinsky, and Sully sort of actually proposed a thought experiment that allows you to witness this monogamy of entanglement violation. Oh, I did not say what's the problem. So I said before that this qubit B needs to be entangled both with the system H and with the system R. And this is impossible because of monogamy of entanglement. We know that no quantum system can be maximally entangled with two different systems. So this is the problem that we're trying to overcome. And sort of what the firewall paradox actually attempts to show is that this violation of entanglement is sort of effective. You can actually witness it. And they're doing it in a pretty simple way. So if you're inside the black hole, then you cannot go out. But if you're outside, then you can certainly go in. So they were proposing the following. So we have Alice, and she sits outside of the black hole. And she collects all the radiation that's emitted from the black hole. So she has access to the register R. And also, she knows the laws of nature. So she knows the process that created the black hole and sort of controls the radiation process. This means that Alice can actually distill a qubit D out of register R that is maximally entangled with B. So this is sort of the twin, the EPR twin of the next qubit that's going to be emitted. Now Alice waits for this qubit B to actually come out. She catches it, checks that indeed this qubit D that she has is fully entangled, is maximally entangled with B, and then she jumps into the black hole and finds the sort of entangled mode, the qubit that's sort of the other EPR pair of B. And this way, Alice witnesses this monogamy of entanglement, and again, sort of we have a problem. And what AMPS propose is that maybe what you need is to sort of change your physicists need to change the way of how they think about the boundary of the black hole, how it behaves. But they don't like to do this for some reason, so they try to find other ways to resolve this. This sort of paradox. And one way out, which is interesting to us, was proposed by Harlow and Hayden. And they noticed the following thing. So in order for this experiment to work, Alice needs to be able to sort of distill the qubit D out of register R sufficiently quickly before the black hole it continues to radiate and shrink. She needs to do it before the black hole evaporates completely. And if this distillation task is computationally hard, then Alice is just not going to make it. So you actually cannot conduct this experiment under sort of standard circumstances. So this to us sounds kind of like cheating because it's like, well, you're not going to have enough time, so let's not worry about it. Where the problem in some sense is still there. But physicists, or at least some of them, are kind of are okay with this sort of solutions because they know that they don't have the full theory that sort of describes black holes. You need actually quantum gravity theory, and they don't have it. So it's enough for them to have sort of this effective description that talks about what happens in normal circumstances. So if in normal circumstances you don't see sort of anything weird happening, then when they figure out what quantum gravity, they'll figure out what happens when when you can distill this this qubit. So this is the idea. I don't want to get into that too much, but we want to think about sort of the computational aspects of this decoding problem. So let's sort of zoom in and be a little more specific about this black hole radiation decoding problem. So the setup is the following. So we have the laws of nature have a way to efficiently generate the black hole. So it's this 3-register state, H, B, and R, where B is a single qubit. And we have a promise that B and R are maximally entangled. So there exists a process that could be inefficient that takes the register R and distills the qubit D out of it. So it distills the qubit D such that B and D are actually an EPR pair. Now, given this setup, your input is access to the register R, and what you want to do is to be able to come up with a register D such that B and D are correlated. And in prior work by Harlow and Hayden and by Aronson, it was shown that sort of perfectly recovering D, so recovering D that is sort of really in an EPR, the EPR partner of B, is computationally hard under some assumptions. So what do we do in this work? Well, we started by showing sort of a more quantitative definition of the black hole radiation decoding problem. And this allows us to show an existential equivalence between the hardness of the radiation decoding problem and some quantum cryptographic primitives. And these cryptographic primitives are both useful, so you can do stuff, you can do cryptographic stuff with them. And also they're potentially weaker than one-way functions. So it may be possible that these quantum cryptographic primitives exist, even if one-way functions do not exist. More specifically, we showed that the radiation decoding problem is hard if there exists, hard instances for the radiation decoding problem exist, if and only if there exist these EFI pairs, or equivalently, there exist non-interactive statistically binding quantum commitment schemes. So I'm going to say a bit more about this in a minute. So these EFI distribution pairs, this is just a pair of distributions over quantum states, and they're efficiently sampleable. So these two distributions are efficiently sampleable. They're computationally indistinguishable, but they're statistically distinguishable. So if you have unbound computational power, then you can distinguish. So it's a very basic primitive, but it's known to not only be equivalent to non-interactive statistically binding commitments, but to a bunch of other quantum cryptographic primitives, such as other types of commitments, oblivious transfer, multi-party computation protocols, some types of zero-knowledge proofs, and sort of a bunch of things. So what we actually show is two things. So first of all, even if you don't believe that one-way functions exist, there could still be a computational reason why you can generate these instances where radiation decoding is hard. In the opposite direction, perhaps more interestingly, if you believe that there should be a computational restriction, so that the reason why you don't see this violation of monogamy is for computational reasons, then you should also believe that quantum cryptography exists, like all these sort of nice cryptographic applications should also exist. And I'm going to talk a little bit more about like sort of philosophical implications down the line. But for now, let me tell you one more thing that we do, which is amplification. So you can think about two variants of this problem. An easy variant where you just need to find some non-trivial correlation between this qubit D that you find and the qubit B. And the other that you really need to find like a near EPR pair. And we show, well, that these things are, again, existentially equivalent. So if there exists an instance for which the hard variant is hard, then there exist these EFI pairs. And if there exist EFI pairs, then there exists some instance where even the easy variant is hard. So let me tell you briefly how we do this. So in one direction, we assume the existence of non-interactive statistically binding commitments. So these are quantum commitments, but they're committing to classical bits. And again, these plausibly exist even without one-way functions. And we want to create a hard instance for the radiation decoding problem. So what do we do? Let's start by sort of assuming that we have a commitment not to classical bits, but to qubits. So we have a quantum commitment scheme to qubits. And we're going to generate qubits B and D just as an EPR pair. And then we're going to apply our commitment scheme to the qubit D. And finally, the commitment part is going to be the register R. And the opening of the commitment is going to be in the register H. In this way, we're going to create an instance, H, B, and R. And we claim that this is a hard instance for the radiation decoding problem. So what do we need from the quantum commitment scheme in order for this to work? Well, first of all, we need to be quantum statistically binding, in the sense that if you have unbounded computational power, then you can recover the committed qubit D out of the register R. The second thing that you want is to computationally hide all information about D in the commitment. So if you computationally cannot recover any information about D, then in particular, you should not be able to recover D that is correlated with your input B. And how do you achieve this? How do you get this qubit commitment from a bit commitment? Well, it's not very hard. You use quantum one-time pad and just use the commitment to classical bits to commit to the key of the one-time pad, which is just classical. So this is more or less what we do. Now going to the other direction, going from quantum gravity to quantum cryptography. So our goal now is so now we assume that there exists a setting where the radiation decoding problem is hard, and we want to create this EFI pair. So we want to create two distributions that are computationally indistinguishable. In particular, we are going to need to show a reduction. So we need to be able to use an adversary that breaks our EFI construction and use it in order to solve the radiation decoding problem. And that's going to be a little bit hard because the EFI is just a distinguisher between two distributions. So its output is a classical bit. However, in the radiation decoding, the output is a qubit. So we need to be able, our reduction is going to need to be able to translate from sort of getting classical information from the EFI adversary to actually being able to solve a quantum problem. And so indeed, we do this. So we show that you can find classical hardcore bits for the radiation decoding problem. And our intuition comes from, well, teleportation or super dense coding. You can think about it in different ways. But essentially what we do is sort of we set up our EFI distributions in such a way that an adversary that distinguishes these distributions is actually sort of secretly, without knowing, teleporting the qubit D into some other qubit that's in our control. So we create an EPR pair and sort of embed one half of it in our EFI challenge. And if you distinguish our EFI distributions, then you're secretly teleporting the qubit D into a qubit that's in the reduction's hand. And then the classical output of the EFI distinguisher is really just the classical information that you need in order to complete the teleportation process. So there's some technical details that I'm going to spare you, but this is more or less what we do. And then we, in order to show the amplification, we essentially use parallel repetition. So these are sort of the results. And let me spend a couple of minutes talking about this sort of theme of trying to justify cryptography using physical phenomena. And to be concrete, let's talk about one-way functions. So one-way functions are these functions that are computationally easy to evaluate and computationally hard to invert. But what do we mean by this sort of notions of computational complexity? Well, these are supposed to somehow capture the amount of physical resources that are required, like time and energy, that are required in order to perform this computational task. So how much time and energy do you need to compute, and how much do you need in order to invert? So why do we think that the one-way functions exist? So one reason is that there are some mathematical problems that a bunch of smart people tried to solve for a very long time, and they were unsuccessful. So we're saying, well, they're probably hard. So let's try to construct one-way functions based on the hardness of these problems. And that's fine. But it's possible that we're just, that we're being silly, and these problems are not actually intractable. But we do what we can. There's another path that you can take, which is that we can observe in nature a bunch of processes that seem to behave in sort of a one-way fashion. So you can think about sort of scrambling an egg. This is something that does not take a lot of time and energy to do, but it's going to take a huge amounts of time and energy in order to invert. So we observe these things in nature, and we say, well, if these things happen, then possibly one-way functions exist. And again, there's the possibility that we're being silly there as well. So maybe there is an efficient way to sort of unscramble an egg. But these type of conundrums are actually we as humanity actually have a way to deal with them, and that's called science, right? We don't just say, well, it seems like it's hard to unscramble. What we actually do is to come up with like these set of laws of nature, and we verify them with experiment and with observation. And we sort of should be able to deduce from these laws of nature, for example, like the second law of thermodynamics, that certain processes should be hard to invert. So this is not actually a proof that like your candidate one-way function is secure, because, well, the laws of nature are just our current, say, best conjecture for how the universe behaves. But it's kind of a different way to get some independent evidence that maybe you're doing something right. Like these objects like one-way function could actually exist. And sort of what we see here, and perhaps in other places, is that these sort of high energy physics phenomena or quantum gravity actually provides you with like a pretty nice and useful interface to sort of try to get these kind of derivations, whether you believe in them or not. Yeah, so this is perhaps something to think about. Now to conclude, well, these hard problems, they come up in nature. It's possible they're essential for some reason. As I said before, well, you can think about them as some sort of an argument for cryptography. Harlow and Hayden concretely suggested that computational hardness could sort of censor the violation of entanglement in this firewall paradox experiment. In this work, we showed that sort of the opposite could also be the case. Sort of if you believe that computation should censor this violation, then you also get cryptography out of it. And it's interesting to see whether it's possible to find this kind of phenomena elsewhere. So thank you. The paper's on arXiv. I didn't put the link, but I'm sure you can find it. Thanks. If you try.
Great. We have plenty of time for questions. So field them up here at the mics.
So here's a tip. Don't get swallowed by a black hole. Let's get the questions then.
I guess the question I have is, how does this solve the physical paradox? Because it seems like we would want a result that's perfect, not just computational. You know what I'm saying? Like it should be not recoverable in theory.
Right. Okay. So like 90% of the questions that I get are actually questions that should be referred to Harlow-Hayden. But I'm still going to sort of try to say what I sort of understand. So again, the point is that they know that they don't have the complete theory. So in extreme conditions, there is some other mechanism that's supposed to sort of pop out and do something, and we don't know what it is, and we don't know what it does. So it suffices for now to figure out why under normal circumstances, so if nothing sort of too high energy happens, then we get a worldview that is consistent with sort of the physical theory that we have. So this is sort of the explanation that I have. And I said in the beginning, this is not completely satisfactory, I think even to the physics crowd, but you know, you need to start somewhere.
Okay, seeing no other questions, let's thank our speaker again. So we've got a brief break now for interchange between